other kinds of models you see, do I buy this thing, or which of the 10,000 English sentences that I could have said did I say? Those have some discreteness in them, and then that gives a different class of models. And so I'm going to talk about the models where actions are in a continuous space, and then Omer's going to talk about models with the discrete quality, and also his are going to have a lot more Bayes rules. Okay, so this is really the DeGroot lecture, because I'm going to at least make my central point that I say everything around the DeGroot model, and I'll tell you about what that is. If you want a reading for this, we put it up on the list of readings. There's in this recent handbook for social networks, Omer and I have a chapter. Sorry, not Omer. Evan and I, Evan Sadler. So Golub and Sadler is the reference, and it's on my website. You can just download essentially the published thing. Don't tell the feds. And what this lecture really is just I wrote out by hand, condensed, what I think are the most important points of that chapter. So let me tell you about the DeGroot model. So the basic setup is that you have some space X in which estimates, or I'll slip and call them opinions, but estimates is the word I prefer. So estimates will lie in this subspace, in this space X, which is just a convex subset of a vector space. That's all it has to be for what I say to make sense. But I will often, without even thinking about it, revert to my favorite example of such an X, which is the 0, 1, one-dimensional interval. But actually, the example DeGroot had in mind himself was the simplex, so probability distributions over some states of the world. So he thought of people as possessing distributions, like a bunch of statisticians are trying to, think about the weather tomorrow. Each of them has a distribution over what it might be, and then the natural elements to think about as estimates are distributions over that. So this model has a lot of history. The sociologist John French, I'll tell you, let me actually, before I say, stuff about the history, let me tell you what the model is. The very basic, in stick figure form, each individual has an estimate at each time, t equals 1, 2, 3, and so forth. And the updating rule is simple. The way you decide what to think or do tomorrow, or I guess let's make it as written today, t today, is a weighted average of stuff other people are doing yesterday. So in DeGroot, the way DeGroot talked about it, these are statisticians. They have other statisticians that they respect, whose estimates they pay attention to, whatever. And the way they form their next period estimate is by doing this linear opinion pool. So I'll discuss lots of motivations later and I warned you that the math lecture on the first day was a low motivation zone, but here we're back. This is not a low motivation zone. So I'll tell you ways to think about this economically, but let me just say what the model is. Is there a question?
Is the weight exogenous given, or you update his weight? Because, for example, after some period, I thought this expert more smarter, or this expert is dumb.
Very good. This question is, if we have talked for a while, and implicitly in your question, there's the idea that I realize that I do see the ground truth. I see something about the process we're trying to figure out. I may see that you're always off the mark in your announced estimates, while Eric is always saying exactly the right thing. And then it would seem that I should adjust my weights to take that into account and put more weight on Eric's estimates than on yours. And you can indeed study models, variants of the DeGroot model with that feature, and I'll mention them. But for a while, to get a feel for the mechanics, we'll take the W to be fixed and exogenous. And I should also say relatedly that the initial guesses, the initial estimates we start from are just taken to be an exogenous arbitrary vector. That's a strength, not a they could obviously be whatever you want, and then I'll tell you how to study the evolution of these x's conditional on an arbitrary realization of x0. So as already is pretty clear, W is going to be an n by n matrix with non-negative entries. These are the updating weights. And each row sums to 1. So I'm going to impose that because otherwise it's hard to think of this as averaging. And the rule, the features of the rule I want to point out is that it's very simple. It'll become even simpler when I write it, when I start using matrix algebra. It's stationary. You keep using, at least for now, the W's stay the same. So it's really a stationary updating rule. And it's synchronous. This is in the sense that we all, like at 7 o'clock every morning, we wake up and we update. That's formally what goes on in the model. This synchronicity is I think, the least appealing version of the updating. Updating is not really like that, but fortunately it's also the easiest to relax. And so you'll see that you could have asynchronous processes, and understanding what I'm about to tell you in the synchronous case will be the core ingredient you need to understand to make sense of that. By the way, I'm doing something a little weird here, so in terms of how the slides look. So 2 things. If you want to look up close, this is where this is. You can load it on your computer or phone or whatever. But also, if you should feel free to ask me to zoom in. This technology permits me to do that. So here's a really simple case. I've written it a little schematically, but remember the undirected graphs we were talking about the first day. So there's just some graph where there's an edge between a pair of us or not. In that case, for every time there is an edge, whenever it's possible for me to pay attention to you, we can make the weight I put on you to be 1 over the total number of neighbors I have. That's a very simple special case of the DeGroot model, which is just straight averaging of neighbors. But of course, you could have neighbors that you pay more attention to. So it doesn't have to be like that. Let me give I'll give an animation to show you schematically how this process looks. Let me mention quickly history. So the sociologist French had, this is we cite it in our survey so you can look it up. It's a fun paper to read. He talks about these laws of physics of interpersonal influence. He's like, well, people are pulling you in various directions, and there's some principle of some Newtonian, balance. And he really takes it seriously. It's quite a trip. So he, and then after him, the kind of sociological graph theorist Harari played around with model versions of this model with this uniformity built in. They didn't even consider relaxing it. And then DeGroot came along. I forget whether he was aware of them or not, but he basically did what any of you would do. He said, aha, okay, he realized the general that this, you might as well study the general form with general weights. He sort of said everything in the correctly general language involving Markov iteration and so forth. And so in part that's why it's named after him. Fun fact, this is one of the 3 or 4 papers cited in Aumann's Agreeing to Disagree. So at the very least, this paper has high eigenvector centrality. So if you want a picture to remember for yourself of how DeGroot looks, suppose we have this network. Don't pay so much attention to the colors and stuff. We'll come back to that later. But just think of these as, think of this as an arbitrary graph. And these bottom guys start with an opinion that's, let me say black is 0 and white is 1. So these guys start with a low opinion up in the 0-1 interval. These start with a high opinion. And then what happens when we run the process? Well, you see the color will spread, right? So these guys, the guys who have contact with an opinion different from their own, they average. This guy averages, I've done equal weighting here. So this guy is less dark than this guy because this guy has more white neighbors. So you can iterate it. You see the color spreads out. By this time, everybody's been a little bit infected by the opposite color. And then after 10 rounds, you can see that it's really started evening out. Although it's still pretty clear, if I hadn't done the optical illusion coloring, that this top is a lot lighter than this bottom. So after 10 periods, substantial differences still remain. So later we'll think about, it's not an accident that this has some sort of homophily or group structure built in. So just to sort of preview what's interesting, we'll be very interested in how group structure of the underlying graph translates into the behavior of the updating process. But let's do some basics first. So back to, this is the slide we had already. So the weight, so Wij says, how much does I care about J's opinion? So the arrow, an arrow from me to you represents a relationship of trust or attention. If you look at this picture, there's an arrow that you might naturally draw. Which way is influence flowing? Which way is the color? Which way is the black color going? And that's the opposite of the direction. So if I influences J, then the arrow is in the opposite direction. So it's just good to be reminded of that. Okay, so I'm going to discuss foundations after I get done with this column, and I'll tell you why an economist might have written this model down. There are a bunch of variations too. You don't have to be able to read this, although I guess I'll zoom in to make it. There are a bunch of variations that some people will surely be moved to suggest, at least in their minds. So you could think about time-dependent weights. That's already been suggested. It turns out that's how you make this model consistent with correct Bayesian inference in some sense. I'll tell you more about that. You could think about stochastic meetings, get rid of the synchronicity where for sure I see the same people and update from them at 7 a.m. every day. You could do it in continuous time where I wake up on a Poisson clock and that's when I update. You could have a persistent own estimate. You can convince me some about Donald Trump, but not all the way. And we can think about discrete rules, like I have to do action 1 or 0, and the way I'll decide which is to take a majority poll, let's say, of my neighbors, or some kind of weighted majority. That's Omer's lecture. That and a lot more you'll see in Omer's lecture. That's called the voter model sometimes, because it's as if you run a little election. Okay, so as some of you have already noticed, you can rewrite this updating rule, which I've written for one individual, is now if x is a vector, it's x equals w to the power t times the initial estimates, right? So one step of the rule in matrix form is that's one step where I've just used matrix notation to condense this, and then you can enthusiastically turn that crank and arrive at this expression. And then it becomes clear that to understand the dynamics of this process, what you really want to understand is the dynamics of matrix powers of W. So let me give you two interpretations so we really need to think about this matrix powers of W, so let's think about what that guy is. One interpretation of it, which is just read directly off this equation, is that the ijth entry of W to the tth power is the slope of Mr. I's estimate at time t in the initial estimate of Mr. J, right? So I'll write that. This is worth... I'll put two things up here and I'll zoom in again. Okay, so this is just reading from this equation. You can just see that this expresses xt as a linear function of x0. So what are the slopes for each pair? A little more interesting and connected to the stuff we were talking about on the first day is this other expression for those entries. Here, I'm saying that the ijth entry of W to the power t is a sum over what? Over walks of length t from Mr. I to Mr. J. Remember, arrow here is attention, so it's walks where I'm paying attention to someone, blah, 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 who's paying attention to you. And if you sum over all walks like that, the weight of the walk, I'll tell you what that is in a second, then that also tells you that entry. So this entry, in a sense, adds up over all the conduits of J's t-step influence on Mr. I, the strength of that influence, right? The ways that you can change my opinion is to change someone else's opinion, who changes my opinion. This adds up all the ways to do that and weights it appropriately by the, of course, linear factors that are involved. So to be clear about what I mean by these weights, the weight of a walk that is the weight of a typical walk here is just the product of the W's as you go along that walk. So if there's a walk where I trust Eric, who trusts Elchanan, who trusts Matt, I just add the W's along every edge of that walk, and that's the contribution of that walk in this sum. I multiply the W's. So the weight of a walk is the product of all the edge weights involved. And just to do that let me just put up a concrete example. So here, what I've done is I've drawn a little graph where Mr. 6 pays attention to Mr. 2 indirectly in 1, 2, 3 steps. And so if we want to know how much Mr. 3 weights Mr. 2, well, there are 2 walks of length 3 from Mr. 6 to Mr. 2, this one and this one. And indeed, it's true, you can check that the entry of W cubed is the sum of the weights of these 2 walks. And again, as I said on Monday, that's just matrix multiplication. Now, so that's it for that example. Now, those of you who know about Markov chains may already have thought to yourself something like, this is a Markov chain. Be careful, don't think that. If you want to know what the Markov iteration really is, it's pi. So pi of t. Pi is now a vector of occupation probabilities in a chain. You have a chain. It starts somewhere, and you want to know how likely are you to find the chain at every state at period t. And indeed, it is true that you can write the row vector of these occupation probabilities as the row vector of initial occupation probabilities times w to the t. So it's certainly true that in some sense it boils down to understanding w to the power t. But there is a big difference, as there usually is in linear algebra, between doing something on the left and on the right. So many of the casual things you know about Markov chains, like for example that the sum of entries in pi is conserved, that's not going to be true about the process when we do it on the right. So on the one hand, realize that everything you know about w to the t from Markov chains does hold, but you have to be careful how to apply it to a process that is in some sense dual to the original process. Now, if you want to know what this really is in terms of Markov chains, I'll tell you. This is just for fun, and I'll say it quickly. So this last bit isn't important to understand, but for those of you who care, you might find it amusing. You can give an exact Markov interpretation. So let's suppose we have a Markov chain, and we label the states by various numbers. So yj will be the number that labels state j. And suppose I do the following exercise. I start at I, and I make transitions according to my Markov chain for t steps. I get a random variable describing where I am after t steps, right? There's a lot of randomness in the steps, but zi is the whole stochastic process, starting at I at period 0 and then going wherever it wants. Now what you can ask is, hey, I wonder what the expected label will be where I end up. Okay, so you took a walk, maybe in this chain, maybe you went this way, maybe you went this way, who knows? And you want to know what's the expected label of the node where I will find myself after t steps. I've written that like that. That's the expectation of y, which is the label function, sub where you end up. So the randomness is all in the subscript. It turns out that the DeGroot process tracks that thing. Okay, so it's the expected value of a function of a Markov process. So you can write this y is a function of the state space, and if you want to know how an expected function of the state behaves as you take steps in a Markov chain, you get the DeGroot iteration. And so in books like this, so I recommended a book on linear algebra. If you want to know kind of a really nice exposition of the state of the art in Markov chains relevant to what we'll talk about, I recommend this book by Levin, Perez, and Wilmer called Markov Chains and Mixing Times. It's a little textbook, very accessible, free online, and has a bonus Israeli flavor.
So for that purpose, what yj is a point in Rn.
Well, yeah, it's something, any space where you can take expectations. Okay, so that's the basics. Any questions about? So some of this, the left-hand side is about to disappear. So any questions? Yeah.
Sorry, so 2 is listening to 6, right?
No, here 6 is listening to 2.
Okay, 6 is listening to 2. Is he conditioning on, okay, I'm listening from both paths, the signal? The difference between the Bayesian and naive learning that we saw yesterday.
Yeah.
Whether I'm listening the same
Yeah,
from several sources or not.
So for a while, this is going to be the benchmark most naive model, where, so it doesn't have to be, everything I'm going to tell you is valid for arbitrary W. So in some sense, we're committing this agent, I'm not sure why, but we're chaining him down to use the same weights over and over again. A rational agent would make adjustments because he's already learned some stuff. If you know, say you're my one friend, right? And I'll come back. Actually, I'll answer your question completely in just a moment, because we're going to do foundations, and I'm going to discuss the learning foundation, which is relevant to, for example, what Adam talked about in the second step. But first, I'm going to tell you about a game foundation. So this is, you can think of the DeGroot model as a very simple, in fact, too simple, but let's try it. Myopic best reply dynamic in a game. So suppose you have a bunch of agents playing a straight coordination game with the nicest possible payoffs. Let's just take their actions to be real numbers for simplicity. And then, you know, you can say, so this is their payoff. If you think about it for a moment, you'll realize the best response. So if you were to be a myopic best responder and look at your neighbors and see what are they doing, I'm going to assume they keep doing that forever. And I'm just going to best reply to that as my next action. You're going to get linear best responses. That's why God gave us quadratics. And then if you iterate that with, you know, it'll be these weights. And then if you iterate that, it'll be exactly the DeGroot dynamic. So if you start somewhere, if you start at some actions, and then you let people who care about coordinating with their network neighbors update repeatedly, you're going to get the DeGroot process. So that's a very plain and, you know, some people like to study learning rules that are deliberately kind of too simple, and this gives us a way to analyze quite a lot of depth. One of them, I want to put an alternative, which is a good place to mention this kind of thing. So rather than a really pure coordination game where you just care about coordinating with your neighbors, you know, one thing to say about that is that any coordinating on the same thing is a Nash equilibrium, no matter what that thing is, right? So no matter where they start, it's going to turn out this is going to take them to a Nash equilibrium, but which one? Well, it depends on how people started, okay? Now you may think that there's something nailing down actions that's not just, you know, it's not pure coordination, but there's something external that controls what we'd like to match. So a way to model that is you can take a utility function that's a mixture of the pure coordination payoff with some weight strictly between 0 and 1, and then have another aspect. Oh, so this is a mistake, by the way. There shouldn't be a minus here because there's already a minus in this payoff. So you get a penalty for miscoordinating. Just think of UI being the summation here. You get a penalty for miscoordinating as before, but now you put some weight on coordinating with some BI, which is your private best action that you like to take, that you would take sort of in isolation. So you can write down that dynamic, and then you can write, the best response will still be linear, but now it'll involve these BIs, right? And it turns out that if you write out where people will converge to after doing myopic best reply for a long time, they'll get this x infinity, which is basically a weighted average of W to various powers, and then times the initial estimates. So it's sort of like you ran a bunch of DeGroot processes for different steps, and for different amounts of steps, and then you mix over where you get, and that turns out to give the right. You run the DeGroot process starting from this vector of B's, which is personal favorite actions. You do it for 7 steps. You know, that term participates here. So this is the Friedkin and Johnson model, because they thought you have some persistent, you know, you have your mom at home and she's always saying the same thing. She's never influenced by anyone, so she's always in your updating persistently. And so if people have moms who say different things, there'll be a gradient of opinion in society. You won't all converge to the same thing as you would in a pure coordination setting. And this gives you a formula for how to average all the moms.
update their information, or because their goal is to be consistent with their friends. It seems to me two very different stories. What is my intuition?
I strongly agree with what you said. Those are very different stories. And there's nothing forcing us to collapse them into one. So there are two separate stories. There's a utility coordination, there's a utility-based coordination motive, and then this is the sense in which this model is appropriate to that. There's also an informational motive, and this model will turn out in a certain sense to describe that with some behavioral restrictions. But if you want to tell me, if your question is which of these is the case, I would say that question doesn't make sense. Sometimes one is the case, sometimes the other is the case. So you have to think about your problem and decide, are they coordinating for pure coordination reasons? So I'll tell you, when I decide what software let's say what language to use, I'm mostly driven by coordination. There are some languages I prefer to English, but I have to give this lecture in English. Other times I'm really trying to learn about what the best presentation software is, and then it's informational. And there may not be much of a, I can use mine and you can use a different one. So you want to say more about your question?
So your current model is that you wish to be consistent with your friends, but the first model that you presented in the lecture was of learning that I update my information.
Well, the first model I presented is this humble object. I would say this has no economic content. It's just a piece of linear algebra. We can then impose economics on that and say, will certain kinds of estimates obey this rule of motion? Will certain kinds of, coordination-based updating rules? But this, let the math be. This process makes sense without any interpretation. So I don't think on the first slide I gave a learning story. I mentioned one tangentially, but conceptually I want to say this is a mathematical model. We want to study its properties, and then we want to think about a whole family of interpretations. Well, it's social science interpretation of a mathematical model. So I'll now show you so let me say the second part and then we can come. But yeah, I think I would say that the second thing is going to be, a micro foundation, a little auxiliary model that's going to help us think about this law of motion as a learning, because here there's no learning. You can say, actually confusingly, people call this learning in games, but it's only learning about what other people are sort of doing, like learning the equilibrium, right? But then there's learning about stuff you want to know about the external world, which matters. So the second model is a learning model in that sense. And this formulation is due to DeMarzo, Vallanos, and Zwiebel in a paper of 2003, which we cite in our survey. So suppose there's some true state of the world mu. Let's suppose that individuals have initially a prior belief about it, and let's assume that belief is diffuse. That's just for convenience. But we start with very diffuse normal priors. Fortunately, though, we get a signal at the beginning of time. So this S is... sorry about this jumping around. I may switch to my PowerPoint. But hopefully it'll behave from now on. Oh, I know what happened. I didn't zoom out all the way. Okay. So you have individuals who have diffuse priors, but at the beginning of time they get a signal. Mr. I gets a signal Si, which is the true state mu, plus a random noise, epsilon, which is distributed normal, sigma I. And then, because the priors are so diffuse, approximately, and I'm going to not worry about the approximation, Mr. I starts out, if you ask him to estimate mu, the signal is going to be very much more valuable to him than the prior, so he's going to basically just think that his best guess of mu is the signal he got, okay? So suppose we had everybody form those period zero estimates based on private signals alone, and then we all announced them, and we said, hey, I think mu, so this is a world in which we really care about learning mu, and then someone announces, everybody announces, okay, based on my private signal, I think mu is 26. I say 26, you say 24. Now suppose you want to do one more step of updating. Suppose you say, okay, now I'm hearing some information that's relevant, because these signals are assumed to be independent. The epsilons are independent, so the signals are conditionally independent given mu. And so I just heard some valuable information. Other people think it's different from what I thought. How should I integrate it? So it turns out, it's not completely obvious, but it's a good exercise, that the Bayesian procedure for integrating this information you just heard is to take a weighted average of the stuff your friends said. This is very specific to normal. If it weren't normal, you certainly wouldn't be taking a straight average. But as you can look up in DeGroot's standard book on statistical inference in a Bayesian paradigm or whatever, you can see that in this world, the optimal way to take this information in its step one is to average it in a weighted way that captures the precisions of different information, right? So if your signal tends to be much more precise than mine, then I'll put a lot of weight on yours and relatively little on mine, and these W's will capture that. It's just proportional to precision is the rule for the W's. So this is so far the one step, if t is equal to 0 here, I guess, so this is one step of updating. This is just straight Bayesian learning off normal signals. Now, Demarzo, Ioannis, and Zwiebel had an idea, and now this goes to your issue, which is they said, look, a way to think of DeGroot agents is they just keep doing the same thing even after it stops making sense. In the first period, your signals were conditionally independent given the mean, so it made sense to weight them in this way, with weights proportional to precision. Now suppose I know that two of you talked, and in period one you updated your signals this way. Now your period one statements are no longer conditionally independent. So period 0 is announce own signals. Period 1 is announce what you've learned after doing the averaging I talked about. Now the signals of two people who've talked are not conditionally independent given the state, right? So I can't apply the most vanilla averaging rule. It'll still actually turn out to be a linear rule, but my weights, as the gentleman in the back pointed out, should now take into account the fact that you two are correlated. So if you two are correlated, while I'm getting a third piece of independent information over there, I want to weight that more because independent information is more valuable. So a Bayesian would optimally change these weights over time to take into account the fact that his informational environment is changing. Just as a, Eric?
In fact, if everyone were connected, it would converge right away.
Exactly. So if everybody, if people could see everybody's estimate, there would be nothing to learn after the first step. You wouldn't want to change your opinion because you've already seen all the exogenous information. Demarzo, Ioannis, and Zwiebel in their 2003 paper that Omer and two co-authors then followed up on proved the remarkable fact that even if they're not all connected, if you let them talk for at most n squared periods, then they will actually still all recover the basic stuff by a Giannakopoulos Polymarchakis kind of. They did it in a different model, but it's the same logic, yeah. And so the interesting thing is by optimally adjusting these weights over time, these guys can really like tease out all the information they care about. And Demarzo, Ioannis, and Zwiebel say, well, we don't think people do that. So often in DeGroot papers, you'll read people make a casual statement like, oh, for tractability, we assume that people, because it's so intractable to compute the correct Bayesian updating in the setting I described. It's not true, actually. At least if you think inverting a matrix is tractable, then the correct rule is tractable for your iPhone. But there may be various reasons why we don't think people do it. And Demarzo, Ioannis, and Zwiebel defend this as correlation neglect, that people really, there's psychological evidence that people don't pay enough attention to the fact that information they get is correlated. They weight the same thing that they hear over and over again more than they should. People have also called it echo chambers because actually what I've said is in your opinion, right? If I'm an influential guy, I know like Matt gets up here, says something about, where networks research should go. Suddenly everybody's saying that Matt's rational, but an irrational guy might think, oh, I just got my opinion reinforced a lot. I was really right. But no, you influenced them. That's why they're saying that. So some people call it the echo chambers model. Ben Enke actually finds, Ben Enke was on the market this year from Bonn, and he has a paper in which he rigorously tests correlation neglect in a controlled environment. I don't think this experiment will be like the one to end research in this area, but it's the best evidence that I've seen that people do really overweight evidence that they should know is just a copy of evidence they've already seen. So you can read his paper for the state-of-the-art and experimental study of this. I'm going to skip some further extensions, except I guess I want to say, so I'll just say it schematically without getting into these, because I want to make sure I have time for the meat of things. But yeah,
Just a comment. You imagine agents were doing this by cerebral thing, but they're not myopics, where they're also worried about how what they do now, how that would affect the information they get in the future. And it turns out that even then, you get again, in any equilibrium of this game, they'll all agree in the end and they'll learn different somehow. You get the same result even if you put
that's right. Right, nothing. Still the report. Even when guys are Bayesian, the reporting I've talked about is myopic. You don't try to misreport to mess up others' learning in a way useful for you. But we could allow agents that were nefarious enough to contemplate that. And Omer points out there is now results, which he'll mention also in his talk, that study this in a fully strategic setting and find that these rules aren't actually messed up that much. So
that's a model where you not only want to learn the state, but you also want to place an action against the other players.
it's like you're playing an action against nature every period. You're happier when you match the state. If your payoff is the discounted sum, then it might be that by messing up your learning in a sense, by making you less accurate, I can perhaps get a better payoff stream by guessing the truth earlier. And if you study it in that model. So Omer, as he'll present it, but he has the state-of-the-art paper in a discrete action setting, but on people who are, everybody always declined to study those models where people update repeatedly in a discrete setting and learn from their neighbors and are fully Bayesian. They said that was too hard. Omer said, well, let me roll up my sleeves then. And they have an econometrica paper in which they solved this problem that people thought was too hard. So there's a lot of recent research on the DeGroot model, and I don't have time to talk about it. I want to say that Ali Jad Babaye and Ali Reza Tabaz Salehi and a lot of other people have been working on very cool developments of the DeGroot model. Just to say this in a word, they have a model where information arrives every period. People take that into account in a purely Bayesian classical way. They Bayes update given their prior from the signal. But then when it comes time between periods to decide what your prior is for the next period, they do a DeGroot kind of pooling with their friends. So in an Alman world, people would look at their friends and treat them just like another source of signals and update in a fully Bayesian way. Like, oh, why did you say that? What's the probability distribution over what you say? How will I update my beliefs about the state of the world given that? But these guys posit that in between inflows of new information, you update in a DeGroot way your priors. You pool the prior for the next period with your friend's priors. So that, and this seems like not so economic or whatever, but it's actually in terms of its orthodoxy, it's not so bad, because it turns out that Savage and Harsanyi, if you asked either of them, what do you think the prior really is? I don't think either of them would have taken a hardcore Alman view that it's sort of the prior at the beginning of the universe. They believe that people update, should be Bayesian locally. You come in with a prior, you get some information, and sort of for one piece of data, you're Bayesian. But the real prior that you use is formed sort of this morning in a kind of loose way that may involve, social heuristics or whatever. So,
I'm sure that's maybe Savage has it.
well, Harsanyi, when he talks about common priors, he talks about maybe, what if there's no common prior? Well, maybe you should pool the experts somehow. So he was, maybe that was just rhetorical, but I think he might have been open to that. But I agree with you, less than Savage. So there have been axiomatizations. These guys, you should read these guys' papers for the state of the art in DeGrootery. Okay, so let's show some results now. So let me ask the first set of questions about the DeGroot model that everybody would ask. So I've gotten, that was just, so now back to your, so I would say those two stories are auxiliary social science models that give different kinds of meaning to this law of motion, and they should be considered separately, depending on whether learning about mu or coordinating on actions is relevant, that will determine which of these models you care about. So let's do some housekeeping. I've been already informally alluding to the fact that guys will converge in this model. So formally, the way to ask, I ask two related questions. First, is it the case that an individual's opinion settles down over time to some limit? You're learning over time. In principle, you could never settle down. You could always be fluctuating in your belief. If people do settle down, is it the case that the limits to which they settle down are the same across people? Is there consensus? And if there is consensus, what can we say about that consensus limit? How can we describe what it is they converge to? Can we say anything interesting about it? Sorry. Okay, so it's going to turn out that the most interesting stuff will be in 3. We'll see there's a rich connection between outcomes, asymptotic outcomes of this model, and cool networky stuff, in particular eigenvector centrality, which I already told you about in the first lecture. So let me tell you, let me zoom in and tell you. So we're going to study, it turns out 1 and 2 are good to study simultaneously. So here's the answers, here's the answers to 1 and 2. Whether we converge and do we converge to a consensus. So first let me just point out that even whether we converge is not 100% a stupid question, because suppose Eric and I start out with different opinions about Trump, but we both respect each other a great deal. And so after I hear what Eric says about Trump, I just change my opinion and make it equal to his. So I put weight 1 on him, 0 on my previous opinion. And he does the same. Then we're just going to keep flipping, right? Over, and question?
Yeah, I was thinking that relates to whether or not the transition matrix is periodic or not.
That's right. So periodicity will be an obstacle. And of course so that's an obstacle, periodicity is an obstacle to convergence. And disconnectedness is an obstacle to consensus. If people in this section of the room talk about something and people in that section talk about it and they never have any contact with each other, then we wouldn't be surprised not to see them have consensus. And those turn out to be the only 2 obstacles. So let me tell you, so assume W is strongly connected. You remember what that means from the first lecture. It means that there's an arrow, there's a path of trust going from anyone to anyone else. Then usually you can answer 1 and 2 in the affirmative. What does usually mean, other than cases with periodicity? And those turn out to be in some sense non-generic. So let me give you 2 definitions that turn out to be equivalent. We say a matrix is primitive if there exists a power L such that that matrix to that power has only positive entries. So W is non-negative to start, but it usually will contain a lot of zeros to begin with, because each of us may only listen to a few people. Primitivity is the seemingly strong condition that you can find a big enough L so that everybody has, all the entries of the matrix are positive. So we all place some indirect weight on each other after some particular number of steps of updating, like 546. It turns out an equivalent condition is that if you look at all the simple cycles in this graph, cycles that repeat no nodes, and you look at all their lengths, other than cycles that repeat no links, right? Because then the greatest common divisor of all their lengths is 1. So the cycle lengths are relatively prime to each other as a set. So this is sometimes taken to be a definition of aperiodicity, although another definition of aperiodicity is this process doesn't cycle. Okay, but it turns out that those are the same. So either of these conditions, which turn out to be equivalent, is enough to guarantee that periodicity doesn't happen, and the estimates do in fact settle down, both individually and actually as a group to the same thing. So let me give you the idea of the consensus proof. It's actually both convergence and consensus. So if you're willing to assume, if you're willing to take this condition for a second, so let's say you believe your matrix is primitive, then the way you prove that convergence occurs is to reason as follows. You know that in L steps of updating, the two most extreme agents in society place some positive indirect weight on each other. That's what primitivity means. So another way of writing that is that, okay, so this is a typo. Let me fix it now. This should say t plus L. So I just want to compare the distance between the maximum and minimum opinion at time t plus L versus the difference between the maximum and minimum at time t, right? And my claim is that if the two most extreme guys place weight at least some positive number on each other, then that distance is going to contract by a factor of 1 minus w. It takes a little bit of algebra to write that out, but it's true. So if every L steps we contract by some constant, then doing that repeatedly, you're going to find that the gap between the maximum and minimum goes to 0. So everybody is going to have the same opinion. And then because this process, once we're in a very small, once the gap between the maximum and minimum is small, you can't ever go outside an interval, right? So it's a little bit more work, but then you can show it. In principle, you could imagine that we all believe 1, and then we all believe 3, and we all go back to 1 again. But of course, in DeGroot, that can't happen because the process is so convex. So once you've shown that the disagreement goes away, it must also be that everybody settles down. Question?
So could you remind me what makes positive?
Well, that's the definition. This is we say a matrix is primitive if it has the property that there is an L, so that W to the power L is a matrix with only positive entries. Now, so it's not obvious if I show you the matrix whether it is primitive or not. I'm saying suppose it has this property, then it's definitely true that in L steps of updating, any two agents place at least some minimum positive indirect weight on each other. Does that, I still haven't been clear, so keep.
No, I understand it.
Now you may know a natural question is, this is not a very primitive condition, despite its name. It's not, so, question? Sorry? So W is assumed to be, so this is assumed W strongly connected, so irreducible. Yeah.
Here about convergence, but there is still in the process maybe overshooting compared to the probabilities that you actually output eventually.
To the estimates, right. So it may be that eventually we settle down to estimates a half. I start out believing 0, but after that I update toward 1. So there's no monotonicity in this process.
Are there any conditions for
Yes.
to gradually converge to?
Yes, and in fact we'll see that later. Remind me, if I don't mention it, if I mention this question again when we get to the study of convergence, okay? By the way, if you remember the path, if you remember the stuff about counting paths and adding up across paths, one simple way to generate this condition is to have everybody put some positive self-weight on themselves, okay? As soon as you have that, then basically you can show that implies that once I'm putting some indirect weight on Annie, after that I'll always be putting, in every further number of steps, I'll be putting positive weight on her because of those edges through me, okay? So there's a simple condition that generates primitivity. So now, I will say that for me today, a matrix is aperiodic if in the corresponding graph where you draw an arrow between I and j if wij is positive, in that graph, the GCD of all cycle lengths is 1. So the cycle lengths are, for example, if you have a cycle of length 2 and of length 3, that will satisfy the condition for aperiodicity. The greatest common divisor. So 2 and 3 are relatively prime. So let me say a little more. So that's, now, I just want it to be complete. That is the necessary and sufficient condition. But if you just want a cheap sufficient condition, just have everybody, actually one person suffices, positive self-weight. But let me tell you something, since this is let me tell you a cute little math puzzle that you may enjoy. This is a problem about mailing things. Suppose you have a 5-cent postage stamp and a 7-cent postage stamp. Okay? then there's a number, some amount of dollars, such that any amount of dollars exceeding that, you can make exact postage with your 5 and 7. By a 5 cent stamp, obviously here you're fairly constrained what you can make. I mean, you have as many 5 cent stamps as you want and as many 7 cent stamps as you want, but you only have those two. And the question is, can you make $4.82 exact postage? Okay, I'm not sure, but I know that there is some dollar amount above which you can make any exact postage in cents. Okay, so that's a number theory fact that you may enjoy deriving for yourself, but that's actually exactly the fact that there's a general. Now, of course, you can replace 5 and 7 by any two relatively prime numbers, and then you can actually suppose you might say I have many stamps, but the greatest common divisor of all their denominations is 1, and in that case, this fact still holds, and that's exactly the fact you need to make w to the power L eventually strictly positive. So it's a cute little piece of number theory that shows up in these Markov things. I should say here, the only tricky part is, if you have 5 and 7 and you're allowed to use negative coefficients, you can make any number you want without any restriction. It's the coefficients are positive, as they will be when you're raising a matrix to powers. Question back there?
I have a more general question. Isn't this also double-T of periodicity that we say we alternate our opinions? You like Trump and I like Trump and you like Trump. Isn't this just a consequence of simultaneity of updates?
Yes. So I agree. As you noise the process, as you add a little sand in the wheels, like making it asynchronous, that'll make it that won't happen. So in some sense, it's a distraction, but we might as well understand this model completely. Okay, so just to sum up what we've discovered, if W is strongly connected and primitive, then W to the power infinity exists. For any initial profile of weights, of estimates, there will be a limit estimate that everybody converges to. So there is a sensible limit of this linear iteration. And moreover, I can write, so just, it should be pretty obvious from that expression, if I write, so WT, or x of t, is WT times x0. So what we've shown says that we can actually rigorously say that there is a W infinity, that this also, where that expression also holds. And now, of course, the question that is on everybody's minds is, what is this animal? What is W infinity? What does it look like? Well, I'll tell you, and then I'll explain. W infinity, and this is really where, if you know Markov chains, you just know these facts. W infinity, I mean, first we know it has to be a linear operator, right? Because if you keep applying a linear operator, under boundedness, what you're going to converge to is a linear thing. So that's not mysterious. So it has to be represented by some matrix, and also we know there's consensus. So it must be that everybody that the weights in every row are the same. Otherwise, you might not get consensus for some initial estimates. So we know from what we've already shown that this must be some vector over and over again. And of course, we happen to know what it is. This pi that is every row of this limit matrix is the normalized left-hand Perron vector of the matrix W, which you remember from my first lecture. But that's overkill in some sense. If you think of this W as a Markov process, it's just a stationary distribution of that Markov process. And so we can write the limit estimates, xi of infinity, as a weighted average of initial estimates, weighted by these pi i's, these centralities that different individuals have, which answers our question number 3, right? We asked, what is the consensus? The consensus is a weighted average of initial opinions, weighted by, so, how much does Eric's opinion enter into the ultimate consensus? It's some measure of how important Eric is overall in all his paths of influence, right? So it could be, for example, that Nir has many more direct links than Eric. Many more people directly listen to Nir. But in the end, once you do this for a long time, Eric wins in terms of indirect paths. And so pi I may be very high for Eric, even though some naive measure, like how many direct links he has, is low. That's the beauty of it. It picks up, the part of the network structure that really matters for the long run. And we can, and just to remind you something I've already written out, if you write out a typical row, so what does it mean for pi to be a Perron vector, etc.? It means this matrix equation holds. And if we write out a typical row of it, or typical column, it says Mr. I's influence is a weighted average of the influence of other people, weighted by how much they pay attention to him, which makes a lot of sense in the DeGroot model, because the way you get your influence here is by changing other people's opinion. So you could have sort of gotten there just by thinking, it must be that if you influence a lot of people and you listen to me, so I influence you, I must be pretty influential too, right? I must inherit some of your influence. Mathematically, you can see that this formula holds by the following slightly loose argument. W infinity times another W had better be itself, right? After I've if I do the process, infinity plus 1 should be infinity. So if I've already converged, hitting it with W one more on the right shouldn't hurt. I know that W has this form. I argued that separately. So it must be that a typical row of W satisfies that equation. Okay. So clearly, pi is not 0 because how could it be 0? That would mean that everybody's averaging. So you can never, if it were 0, no matter where we started, we'd all have eventually opinion 0. That can't be. So pi is not the 0 vector. It's clearly positive because there's no room for negative weights anywhere in this process. You can actually show that because of strong connectedness, this vector pi will be strictly positive. It will be the case that but everybody has positive influence because everybody gets some attention from somebody, and so that gets contagion of positivity. So let me just zoom in because I've said a bunch of this stuff, but let me just put it on the board at the same time. Okay, so questions, start with you.
Yeah, did you mention the column sum or the row sum of W is 1, or you do put other restriction of spectral radius?
So the row is just because I say that estimates are formed by averaging other people. The question is, do I assume anything about W like the row sums are 1? And I assumed on the first slide that the row sums are 1 because I take an average of my friend's opinion. But the column sums may not be 1. Like, for example, if more people pay direct attention to Krishna than to Neil with, let's say, to Nir with equal weights, then Krishna will have a bigger column sum. That doesn't promise anything about how their ultimate centralities will compare. Although, fun fact, if everybody's column sums are the same, then everybody has equal centrality. Everybody has equal pi I, and you can prove that to yourself. So let me just now read aloud what's on the board. I've already told you why the fact that pi is an eigenvector centrality makes sense in this context. And it's intuitive. I already said that argument in words. So just now to sum up, the answers to our questions are as follows. Assuming strong connectedness and aperiodicity, individuals' opinions converge to a limit. They all converge to the same limit. And that limit is equal to a weighted average of their centralities. Now I should say, a weighted average of their initial opinions weighted by their centralities. So DeGroot, of course, didn't think in the terms of eigenvector centrality, and even DeMarzo, Vallanos, and Zwiebel didn't. So one thing that Matt and I did in our naive learning paper is we just sort of said as loudly as we can, look, this is cool that this very intuitive, this notion of centrality that sociologists have been talking about shows up for very natural reasons in this iterated updating model. And so and then it turns out the same intuitions that are at work here are at work in other game-theoretic settings where the same matrix powers show up. So that's one excuse to understand the DeGroot model, that if you have this mechanical way of thinking about this iteration, you'll be able to understand the kinds of matrix powers that showed up, for example, in the private opinions coordination game. So the mechanical nature of it makes it easy to think through, but then it has implications for strategic models with richer structure. Any questions at this point? You had a question.
You speak about long run, and I wonder if it is not the long run we are all dead. You can say what is long run?
Yes, I agree that we are all dead, and I will. The complaint is that it may be that for some matrices, these consensus outcomes may not be relevant because we'll not get there. Donald Trump will already be the president, and it'll be time to talk about something else. And so, how long does it take for these consensus predictions to kick in is an important question. I should say quickly, because I probably won't have time to get to the slide where I say this, that this same analysis can be done with stochastic W, where you meet different people at different periods or whatever. And it turns out that by very similar reasoning, by the same shrinking arguments that I gave, except you do them in expectation, you can show that even with random meetings, you'll still get convergence and consensus, now to random stuff that depends on the order of meetings and stuff. But I tried to give arguments. I could have just appealed to some standard Markov chain fact and said, hey, whatever, we have convergence because you can look in a textbook. But I tried to give these arguments that reason in the most transparent way about how beliefs shrink, because they turn out to be the most portable ones that you can take to settings with stochastic W. As long as you can get those shrinking identities in expectation, you can run the same fact, the same reasoning. Other questions? Home stretch, last half hour. So I've just moved that board over, so you'll be able to continue looking at that. So let me very quickly. I wanna zoom through some stuff so I can get to the speed questions and the how long does it take questions that are so important. Let me just quickly give a few statements that I won't be as detailed about. In the case I mentioned before, where you take an undirected graph and you make weights by allocating weight equally among friends, it turns out that how influential you are just is proportional to your degree, okay? So that's a nice and simple case to think about. You might ask what happens if the graph is not strongly connected, and this allows me to clean up something that Sergio raised earlier. So I got confused when I shouldn't have. The definition on the slide of a strong component was correct. A strong component is a strongly connected subset of nodes you can get from anywhere to anywhere else that's maximal under set inclusion. So that's always true. And there's another notion which is more stringent. So here, for example, the closed components are these two guys. These are strongly connected. And then all the singletons here, these guys have arrows to both of the, like this guy has arrows to eventually to both these components, but nobody pays attention to them. So each of these little individuals is a strong component formally, but there are only two minimal closed groups. Those are groups that don't put any weight outside themselves, don't have any arrows exiting them, and are as small as possible subject to that constraint. So it turns out in DeGroot, only minimal closed groups, which is a special kind of strong component, will have any influence in the long run, because anybody else sort of gives away attention, but nobody's paying attention to them. There's a story I like a lot, just a second, which is that a guy apparently, mythically, a Chicago economist was giving a talk at Yale, and people kept asking him questions. They kept saying, at Chicago you always think this, and you guys always say this, and you're so wrong. And after a while of this, he stopped and he said, you guys are all Chicago this and Chicago that. At Chicago, we never talk about Yale. And so that captures the intuition that if other people pay attention to you and are influenced by you, but you don't pay any attention outside yourself, you will matter in the long run. Maybe they won't. So the story about how to analyze this model without strong connectedness is you look at minimal closed components, analyze each of them separately, their own closed worlds for the purposes of the DeGroot model. And then you have to figure out what's up with these guys. And you can do some linear algebra, which I can talk to you about offline, to figure out where these guys will converge, the outside guys. It'll be some mixture of what the strong components think, what the minimal closed components think. Okay. So let's talk about the correctness of, so there we have two big issues to get to. Is consensus reasonable or correct in some sense? And also, is it, how fast do we get there? What's the speed of learning? So in terms of correctness, DeMarzo, Ioannis, and Zwiebel, I think, were the first to frame that question at all. And they said, they framed it with a fixed n, although correct me if I'm wrong, experts. So they said, take a fixed population size. You can imagine a social planner who would have access to all the initial, think about the model I gave with the normally distributed state and the signals about it, the learning about the world model. DeMarzo, Ioannis, and Zwiebel asked, will those guys get it right? If they update DeGroot, with particular weights, will they ultimately come to hold a consensus belief that is equal to what a planner would have thought, who had access to all the initial information and just did the optimal global Bayesian update, being omniscient? And their answer was, generically, no, that won't be the case. What you need is that the centralities, the eigenvector centralities of the individuals, end up being exactly equal to the relative precision of their signal in the population. Why would that happen? Your graph would have to have been very specially designed for that to happen. So they think about correctness and they stop there. But Matt and I, in our naive learning paper, considered the following asymptotic extension of that exercise. So suppose you now consider a sequence. Obviously, if we're going to be asymptotic, we need a sequence of something. So you're going to have a sequence of societies. Society number n has n people in it. And we're going to just assume that they're all convergent, so strongly connected and aperiodic. And we're going to give people signals just like in the basic model. So initial estimates are going to be the true state plus some independent noises, okay? And we're going to assume that the noises, even as we grow the society, are bounded above and below in terms of their variance. So the variance of the noise doesn't explode as we grow the population. The population's getting bigger, but individual estimates are sort of, not going too wild. And we asked the simple question, if you look at so now we're going to take two limits. Within a society, we're going to take the long run limit and see where these guys converge to in terms of estimates. And then we're going to take across populations the limit of, as we look at bigger and bigger societies, what happens to that consensus in each society? Does it hold that the consensus estimate is going to the truth, mu, which is where everybody's estimate is centered, right? So if we had very symmetric networks, like where everybody had the same weight, it's just the standard law of large numbers, whatever law of large numbers you like will tell you that as society gets bigger and bigger, we're taking averages of these noisy versions of the state, mu plus noise. So of course you'll converge to the truth, but then these networks, they make it asymmetric. So is it, when can we say that people will, even in large networks, despite the fact that the learning process gives some people more influence than others, when will you still converge to the truth? And we answered the question in the way that you also would, having seen what you have seen in this talk. You don't even need to be able to see this because we already know what the consensus is. It's a weighted average. So I'll zoom in on the answer and then I'll zoom in on this other stuff. We know the consensus is a weighted average, weighted by centrality of initial opinions. So if you think about it for a while, you will agree that what's important is that the maximum influence of any individual should be decaying to zero, right? If no matter how big society gets, Elhanan has the network is structured so that half of everybody's estimate is Elhanan's initial estimate. Obviously, you're not going to converge in probability to the truth because his idiosyncratic noise is going to be in everybody's ultimate consensus estimate. But if if influence decays, even if his decays relatively fast, or relatively slow compared to mine. So he's 1,000 times more influential than me, then he's 10,000 times more influential, but all those numbers are decaying to zero, then a weak law of large numbers will hold and will guarantee that it's still the case that all estimates converge in probability to the truth, to mu. And just to be complete, the argument here is very simple. You just order the agents with the most influential first. You can write that here I use a different notation. B is instead of X, but doesn't matter. The variance of the consensus estimate can be upper bounded by, first of all, the variance of any error times the square of times the sum of squares of coefficients, right? I have this formula, a bunch of coefficients times a bunch of random stuff. So by the variance formula, I can bound it by the biggest variance of any term times the sum of the squares of coefficients. That's probability 101. And then if I take out pi 1, which is the biggest pi, so I factor a pi I out of every one of these, but then I upper bound that by pi 1, I can write this, right? I can take out a pi 1, then I just have a sum of the pi i's. But that's just 1, because influences are normalized, right? So that shows me that the variance of the consensus is upper bounded by the biggest, by a constant times the biggest pi anybody has. So as long as I can guarantee that the biggest pi goes to 0, then the variance of the consensus estimate goes to 0. Any questions about that?
If instead of having a bounded variance of the errors, you would have something like as long as they don't grow faster than
Yeah.
with the result.
So once you see this proof, I mean, actually the line before this, but you see what I actually need. This is grossly sufficient. But to your previous issue, you were concerned with why aren't these guys smarter? Why aren't they updating their weights more in response to the fact that the quality of their information in their neighborhood is changing? Okay, they could do that, but the punchline of this paper is even if they don't, even if they're naive, if the network is sort of not too unbalanced in this sense, nobody retains a positive share of influence, then you're going to be okay. And then we said a little more. We said, I won't go into the details of this, but Matt and I wanted to ask, well, what properties of the network will guarantee that? It's not very, in some sense, after you've seen what we already proved, deducing this part is a very, very quick result. So to sort of learn more, we asked, what structurally, geometrically, what should the network look like in order to prevent this kind of piling up of influence on one person? And I don't have time to talk about this in detail, but I'll just say in brief that the answer is if you have a prominent group, which is a group that gets either direct or indirect influence from everybody, and that amount of influence is bounded below by some number, no matter how large the society gets, then there's no hope. You can just see directly that because everybody's getting some direct or indirect attention bounded below by, let's say, 0.02 in this group, their noise will always confound everybody's estimates by at least 0.02, and then it'll never decay more than that. So prominent groups that receive a bounded below amount of attention from everyone, if they're bounded in size, will prevent wisdom, because their idiosyncratic noise will never wash out. Wisdom is, by the way, what we call this converging to the truth. But you can give sufficient conditions in the opposite direction, which is that if weights are somehow balanced, so that the weight in and out of a group is not too, the weight in is of the same order as the weight out, at least for groups of certain sizes, and also society is fairly integrated, so that you don't have parts of society that are sort of very far apart, then you can prove that you will get the law of large numbers. So please look in the naive learning paper for the details of that. It turns out to be reasonably hard to give interesting sufficient conditions for the biggest entry of pi to decay to 0. We had all these ideas, and it kept being hard to show. We kept coming up with counterexamples to most of our intuitive sufficient conditions. So if you like Markov, and it turns out that in Markov chains this question doesn't come up. Nobody really cares about this who works on Markov chains. So if you want a math problem that stumped us, try to give nicer sufficient conditions than we could manage to for when, what geometric structure of the network ensures that the most influential person is not keeping a positive share of influence.
What happens if you get any problems?
You could do replicas, yeah. So any kind of replica argument will give, basically, you take a single network, you replicate it a bunch of times, and you connect it in some symmetric way. That will generate the kind of decay you want. Unfortunately, we think those, 38 villages that look exactly the same. But maybe you could do an expectation somehow, replicate with each village being the same in law, right? So that would be more interesting.
I'm getting hung up on this final paragraph, if there's a comment. You're changing, you're looking at bigger and bigger
Yeah.
society. So what do you mean by...
Sorry, that's too loose.
What do you mean by permanent?
I mean a sequence of subsets of a uniformly bounded size with the property that each subset receives, let's do the direct version, receives from everybody at least a certain weight that's also uniform as we grow. So yeah, these are different. These graphs have nothing to do with each other. Okay, so in my last 15 minutes, I want to talk about a question that ties into a lot of stuff that has come up in other people's, both from the very beginning in Matt's introductory lecture and then in a lot of other topics here, which is segregation and polarization and homophily, okay, and how that affects, let's study how this affects this process. So one of the reasons I love the DeGroot process so much is that the influence of segregation comes out very transparently. You can just see it sort of is a good, I think a big part of modeling is finding the right kinds of X-rays. So finding a model where some kind of structure of, in this case, the network, is manifested very clearly in a process, like here's this updating process. So here you'll see this process looks like it was designed to pick up kind of fault lines in the network in a way that I'll show you. So the questions, this goes to the questions about how fast do we get to consensus. And it's going to turn out that homophily is closely related to that. So we understand the limit now, but there are a bunch of questions that we'd like to know more about. Like how long does it take until, in some sense, the difference between the eventual consensus and where we are at a given time is small? Does that happen for t equals 17 or t equals 17 million? Okay. How does the deviation from consensus look? So Nir asked about monotonicity. Does it at some point, do people sort of go monotonically toward the consensus, or can you get fluctuation for a long time? Sort of go overshooting and undershooting. And then relatedly, if there are networks in which for a long time people remain polarized about the issue, what is it about the network that makes that happen? What features of the network account for that feature of the process? So I'm going to focus on a nice special case, not because it's necessary to, but because it's going to save me some words. I'm going to look at the graph case where we take an undirected graph and we make everybody's weights equal across their neighbors. This is Matt Jackson and I have this homophily paper in 2012, and that's the case we study. It does make a lot of things simpler, although it's not. There are many things that can be said without it. But one nice thing that this assumption yields, it's an exercise to show that because this matrix is conjugate or similar to a symmetric matrix, I'll let you figure out what that symmetric matrix is, we can diagonalize, okay? Symmetric matrices are diagonalizable, so we can diagonalize this W, and we can write it as a matrix S on the left, a matrix S inverse on the right, and a diagonal matrix, so 0 except on the diagonal. We have the eigenvalues of our original matrix W. So the first here I actually am already writing it to the power t, so the eigenvalues to the power t. Question? 0, 1, yeah. Although actually it doesn't matter. For what I say, it will still work. It's still diagonalizable, for example. So you can write, so this goes back to stuff that I said too fast at the end of last lecture, but you can diagonalize the matrix, and you can say more. The columns of the S matrix are the right-hand eigenvectors of W, corresponding, the first one corresponds to the eigenvalue 1. It turns out actually to be a constant eigenvector. And then the second eigenvector here corresponds to the second largest eigenvalue. So the eigenvalues here, I've ordered them by magnitude. Turns out they're all real. So I've ordered them from biggest to largest in absolute value. And the rows of S inverse are the left-hand eigenvectors. One of them is our good friend pi. It's the eigenvector corresponding to 1 is the stationary distribution. And then there's some second one and so forth, okay? So take this as a fact from linear algebra, but you can write W to the t in this convenient form. You'll see why it's convenient. It's convenient because I can then write, so from this, it directly follows that the difference between estimates at time t and consensus estimates, this is the deviation from consensus at time t, can be written as, so what I'm going to do is I'm going to take this part, the part corresponding to the main eigenvalue, that's the part that sticks around forever, right? Because 1 to any power is 1. So that part never dies. All the other eigenvalues, at least assuming aperiodicity and irreducibility, are less than 1. Okay? So they're all the rest of this matrix is going to eventually die. Only the dominant, only this one part will remain. But you guys asked about, can we estimate the rate of this process? So what should we look at? We should look at how fast this bit dies, the lambda 2 part dies, because that one is going to die slower than any other lambda to the power t. So, if just by writing out the lambda 2 component, think of this, I can split this as a sum of the contribution coming from this eigenvalue, this eigenvalue, this eigenvalue, split this up into a bunch of separate matrices, and the part that's coming from the second one will look like lambda 2 to the t, that's how big it is, times this eigenvector times this eigenvector. Okay? So that's the leftover part. That's the part that that's a bound on. So what have I written here precisely? There's also something else, of course. There's the contributions coming from all the other stuff. Okay? That's order of lambda 3 to the t. Okay? So in principle, lambda 3 could be just the same as lambda 2. That wouldn't be very good. But assume generically that won't be the case. So everything else will die faster. So the part of disagreement that is the longest lived is the part coming from the second part of the spectral decomposition. Okay? The second component. And then we want to understand how that thing behaves. Now, to Nir's earlier question of, do you have monotonicity? The answer is yes. So notice so what is this? This qt times x0 is a number, okay? So it's just the dot product of q with the initial estimates. So that's a number. Therefore, the deviation of Mr. I from the eventual consensus is proportional to pi, where p is the right-hand eigenvector corresponding to the second eigenvalue. So that's important enough that I'll write it in chalk. Mr. I's deviation from consensus is proportional to pi, where pi is defined by this. W, or p, the vector p, is the right-hand eigenvector of W corresponding to the second eigenvalue. So this is Demarzo-Vallanos and Zwiebel's result. I mean, to point it out that it's important. This means that eventually, after the third and larger spectral bits have died away, people are converging according to this part, where Mr. I's deviation is just, he's always on one side of the consensus and he's drifting slowly toward it as lambda 2 gets smaller and smaller. That's not 100% true because lambda 2 might be negative. That would be a sick case to consider. There's actually a mistake in Demarzovianos and Zwiebel, which a guy, Dmitry Tubinsky, later corrected, because they sort of forgot about the possibility that it's negative, and they said some wrong stuff because of that. So don't do that. But in spirit, they're right. What they get is a sort of unidimensional, they get guys lined up nicely, right? So I might be, if my P is very negative, I'm very left wing, okay? And if my P is very positive, I'm very right wing. And I'll always be, once this process settles down, I'll always be on that side of the issue. And I'll be drifting slowly toward the center. So we'll be contracting in this orderly way. So we know a lot about the structure of how we drift, and we know the speed, at least as a piece of linear algebra, the speed is controlled by lambda 2, the second largest eigenvalue, which MATLAB will compute for you. But, so just to say that in words, so the closer lambda 2 is to 1, the slower your process is converging. So to the question of are we all dead, it depends. Sometimes in graphs that are realistic, for example, expander graphs that are very popular in Jerusalem, it's the case that even if the graph is very large, lambda 2 is not big at all. And so you converge quickly, okay? But it may be that the segregation is so severe that even though you have consensus, it's basically as if you had, take a disconnected graph, connected extremely weakly, 1 over 10 to the 1 million. Then it's in fact, for any purposes that you care about, it's as if you're studying two disconnected processes, right? And then lambda 2 will be extremely close to 1. Okay, so the last thing I want to say is a favorite subject, which is, the slogan is, lambda 2 is high when the network is polarized, or when it's polarized as opinions are polarized, when the network is segregated, when you can split it into pieces so that these pieces pay little attention to each other, okay? So without time to be complete about this, there's a thing called the bottleneck ratio or Cheeger constant. You can read about that in the Levin-Perez-Wilmer book that I mentioned. But basically a bottleneck is a part of the graph where the weight between, so it's a set M, where relatively little weight exits the set. So that creates a bottleneck. It's sort of, you should think of a picture like this, right? There's extremely little listening going on here. This is a suitably normalized way to measure that, and a whole army of mathematicians who study mixing times and Markov chains are skilled at relating geometric properties like this to whether the chain mixes fast or slow. That is, whether the consensus is reached fast or slow. I want to tell you about something a little more related to what we've been talking about, which is these block models, okay, which is related to these block models. And this is the last thing I'll say. So suppose that we had a graph consisting of an equal number of boys and girls, and I actually build my graph randomly. So I have a large number of boys, a large number of girls, and I link any pair of boys with one probability, and I link any pair of girls with the same probability, but links across happen with a different probability. So there are two numbers here, PS, which is same type linking, and PD, which is different type linking. It turns out that we can relate the second eigenvalue to the, how homophilous that network is in the intuitive sense. So under some technical conditions, we can say that as the graph grows large, the second eigenvalue of W converges in probability to PS over PD minus 1. So if PS is a lot higher than PD, so people are much more likely to link with their own type than other type, then this number will be very close to 1, and then lambda 2 will be large. So that's a simple way of making formal that more segregation means slower convergence, because we already know that lambda 2, Eric looks troubled. Ignore this part for a while.
You say PS is a lot bigger than PD, second eigen.
It looks like there's...
It looks as though it's going to be a lot bigger.
It can violate. Yeah, what happened there? Well, yeah, so the ratio... No, but Eric is right that there's something I forgot to normalize
Yeah.
by something. It's so there is a I'm all, there's a missing normalization. Oh yeah, so right. So let me say, so this formula is wrong. Let me say what's correct in words. It's basically what matters is the fraction of links in the whole network that are same type links. At least in this symmetric, here expected degree is all, you need to make adjustments in other cases. But if most links in your graph are same type links, then lambda 2 is close to 1.
So is it PS over PS plus PD?
Something a lot like that, yeah. So sorry about the mistake. Yeah, it should be that. Good. Yeah. So I'll write, this is not, don't generalize beyond this. Everything is said correctly in the homophily paper that Matt and I have, but for this, we can say that lambda 2 goes in probability to PS over PS plus PD. Okay. And moreover, to use this fact, that deviation from consensus is proportional to your position, it turns out that in this kind of world, your position, your deviation from consensus will be determined by what group you're in. So there may be some initial noise, but very quickly the process will settle down where if boys and girls start with some kind of different opinions, boys will have one opinion, girls will have another opinion. So girls will be left wing, boys will be right wing, and then they'll converge. So you can determine someone's position from their group. You can show using the linear algebra that people's deviations from consensus will track the group structure, and reducing the behavior of this process to group structure is what Matt and I do in the homophily paper, and we give a lot more elaborate models in which you can still do that and understand the behavior of the DeGroot process in a large random network by understanding it sort of only at the group level. And so I hope that gives you, that was fast. There's a lot more in this literature that I'm excited to talk to you offline if you'd like. I definitely have run out of time, so I just want to say thank you and stop.